So as I look around, here's something pretty common I see. I see some stuff like this. Anybody do this? I saw a lot of this out there, and that's all right. And what this is saying is somehow here to here, from 10 million to 1 million is minus 900,000. And here to here, 1 million to 100,000 is minus 90,000. But if it's a number line, we shouldn't have different segments equal different things. So that's one reason that one doesn't work. That's one I saw out there. Another one I saw out there was something like 1 to the 7th, 2 to the 7th. Anybody do something like that? Anybody do that one? I've seen that one today a couple times. The issue with this is this number line is going like 0, 1, 2, 4, 8, 16, 32, 64, bigger number. That's not individual tick marks. Did anybody have a different one that they did? This is intentional, like a lot of people get this wrong. It's cool if you got it wrong. Zeph.
I did 10 to the power 7 times 1 times.
Oh, because you broke it up. So, so let me show you essentially what Zeph did. And this is what I like. This is the first way to think about it, and then we won't probably approach it like this again. 10 to the 7th is really 10 million, right? Right? And I'm splitting that 10 million up how many ways? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 ways. Okay. So, JP, this is an 11th, but its value is 0. Right? Okay, so that's good. So we're going to divide that up equally among 10 things. That means each thing is worth how much? Each 10 million divided by 10 equals what? 10 to the 6th, or 1 million. So I could say that this is 10 to the 1 million. 1 10 to the 6th. Then I would say this is 2 million. 2 times 10 to the 6th. 3 million is 3 times 10 to the 6th. 4 million. 5 million. 6 million. 7 million. 8 million. Oops. I got ahead of myself there. And 9 million. And then my 10 million, I'm going to write as 10 to the 7th. So this is how I could write that number line. Really, this is just by millions. All right? It's kind of like a different visual than we're used to seeing with a number line. But we know number lines have to have individual tick marks. So we can't just make a pattern with exponents. We have to understand what they mean. And if you start here, at least mentally, that helps us see our 1 million each. Right? Are you guys seeing that now? Do we see why the other ones are... This is intended to have a bunch of people get it wrong, by the way. Not to be like, ha, you big dummy. It's more to be like, hey, here's a common misconception. Let's squash it. Let's learn from a mistake. So that's cool. So who can help me point out where 4 million is? Zeph? Yeah, that is 4 million, right? I actually like to think of it like this, okay? How about 5 times 10 to the 6th, Sean?
5 times 10 to the 6th.
Yeah, that one's like good to go, right? That one's good to go. C, okay, so the C's get different. Let's look at the 75 times 10 to the 5th. Meredith? Yep, so right here. So I like how Meredith explained that. She said that 75 times 100,000. Normally we wouldn't say 75 100,000s. We would say 7.5 million, which I like to think of as 7.5 times 10 to the 6th. Okay? This C that's different on the handout. 5 times 10 to the 5th. Who can tell me where that would go? 5 times 10 to the 5th. Ivy? Yep. So that equal to 500,000, which would be halfway between 0 and a million, right? So there's that 5 times 10 to the 5th. 5 times 10 to the 5th is 500,000, which is halfway between 0 and a million. And then 0.6 times 10 to the 7th. What do we have for that? Which one, JP?
I was just saying it would equal 6 million.
Yeah, it definitely would equal 6 million, which is right there. I like to think of it as 6 times 10 to the 6, right? So here's a point I want to make out. What was easier to interpret? All of these in this version or in these versions? Yeah, what was nice about the 10 to the 6th? They were all just in the millions already, right? What do you notice about the first numbers in each of those? Like, how could you explain their value? Every one of them. They're all below what place value? Yeah, I heard it. Was it you, Sophia? Well, just the first numbers I highlighted. They're all below what place value? You're on the right track. You said 10 million, but those numbers specifically without the factors of 10 are all less than 10. Where are all the factors of 10 located in all those numbers that I rewrote? In the exponent of factors of 10. It's much easier to compare these big numbers, okay? I could be like, there's 4 of them, there's 7.5 of them, there's 6 of them. So let's look down here. Number 3, what's larger, 4 million or 7,500,000? Well, it's almost easier to look at it as 4 times 10 to the 6 and 7.5 times 10 to the 6, right? This one's bigger, and it's about double. I'm going to say 2x, about, right? I know it's not 8, but it's about twice as big. That comparison is much easier when we both have them as factors of 10 versus one of each, right? Are you guys seeing that? Yeah, that's the whole point, hopefully. So looking at this second problem on here, we already talked about how getting those all to be just their factors of 10. Looking at this one here, the population of the U.S. is 3 times 10 to the 8, and the global population is 7 times 10 to the 9. And they want to know how many times more people there are on Earth than in the United States. So what's the problem I need to set up here? Ivy? Well, but like I'm just saying, like if I want to find how many times it fits in, what operation am I going to do? I just can't hear because this blown. I think you said it. I just can't hear well. I just can't hear. Division, yeah. So I'm going to take all the people in the world, divide by the people in the United States, right? Now this is a big number, like 7 billion divided by 300 million. But guess what? We know stuff about exponents. So here's what's really cool about these big numbers. How many factors of 10 do they have in common? I hear 9. I hear 8. There's 8 factors of 10 in the denominator and the numerator. And any factor of 10 divided by any factor of 10 is 1. So 8 of these would cancel 8 of those, right? So now my problem is really just 70 divided by 3. Much easier. How sick is that? This problem is 70 divided by 3, which is something around like 23-ish times more people. That means we're not worth very much of this world. That's all right, though. Do you see how knowing some exponent stuff can make stuff easier in life? Big number divided by big number would be much tougher. 70 divided by 3 is really what the problem is. You guys think ice is faster? So to see this, I like to think of diamond as 1.24 times 10 to the 8. So that does mean that ice is faster. It's 1.24 times 10 to the 8th for diamond versus 2.3 times 10 to the 8th for ice. So ice is faster than diamond. I'm going to need your help because my chart's on a different table. So let's label these tick marks. Each one of these zoomed in tick marks is going to be a tenth, right? Are you guys good with this? Because I'm going between 2 times 10 to the 8th and 3. Oh, I doubled up on the 2. It's because I said it while I was writing. So here's my zoomed in portion. 2.5 times 10 to the 8th. 2.6 times 10 to the 8th. 2.7 times 10 to the 8th. 8 times 10 to the 8. And 2.9 times 10 to the 8. Okay, so what's the first thing on the chart? What's the value? 2 times 10 to the 8. And what was that for? What value is that for? Ice? In your table, what is 2 times 10 to the 8th? What? No, what is it? Ice, diamond, copper? It's on your table.
It's olive oil.
Olive oil. So olive oil is right here too. A good drink for a warm summer day. Okay, the second thing on your table, what is it?
I think it's copper.
Space. Space was first. Why did I get olive oil first? Space was right here at the fastest. 3. That's space. They could go 2 places, right? All right, you guys didn't tell me the first thing. Okay, copper wire. Where's that going? Copper wire says 280 million, right? Can I write that easier for my table, my number line I have? Yes. 2.8 times 10 to the 8th, right here. That's copper. Okay. Next was diamond. What was diamond? 124 times 10 to the 6th.
Yep.
So what I'm going to do there is 124 times 10 to the 6th. I'm going to move that over 2 more and make that 10 to the 8th. 1.24 times 10 to the 8th, which is going to be somewhere like right here. So diamond's not in the zoomed in part. Next up, after diamond, we have ice. Matty ice.
Matty ice.
And ice is 2.3 times 10 to the 8th. That's right here. Okay? There it is. So here's all of our things. Again, was it easier to keep them all how they were presented, or was it easier to get them with the same exponent? What was easier to plot? Same exponent if we could, right? Because they're all in the 100 millions. Apparently light is quick. Okay? Which one couldn't get in the zoomed in portion? The diamond. Got left out. And what's faster, ice or diamond?
Ice.
Ice, baby. Because ice is right here in the zoomed in portion coming from this area. Cool. Looking right here. What do we say these all need to be? 1 times 10 to the negative 6. You guys got to be writing this down too. I know I'm going to write faster than you. I can write pretty fast. And one additional factor of 10 gets me all the way up to 10 to the negative 5. By all the way up, that's still a really little number. So there's our tick marks. We got little numbers. So let's plot these numbers. 6 times 10 to the negative 6. I'm feeling all right with finding that one. You guys feeling all right with that? Right there? There's my 6 times 10 to the negative 6. What about 6 times 10 to the negative 7?
6 times 10 to the negative 7 would be...
Is that bigger or smaller than 1 times 10 to the negative 6?
That is big.
It's smaller. It's going to be somewhere like right there. Right? Because that's an additional factor of 10 being divided. That's like, you might want to think of it as 0.6 times 10 to the negative 6. Okay, that wanted to move it to be kind of the same with the same exponent. Okay, what about C? How could I rewrite C to make that easier for us?
Like,
2.9. Yep, times 10 to the negative 6.
Is that the only thing that you can do?
Not the only thing, but look how much easier this is. Almost 3.
Would you do like...
Way easier, right?
Yeah.
And then the last one?
So if you just put out almost 3, then it needs to be simple enough to put out.
The last one, 7 times 10 to the negative 6. A little easier to think
Right
about.
at 7.
Yep. Much easier once I get all my factors of 10 in the tens. Okay? So looking at this, what's larger? 29 times 10 to the negative 7 or 6 times 10 to the negative 6? But we can just compare them on the number line, friends. Which one's larger? Which one of those two things is larger? Yeah. This would be the same thing as 2.9 times 10 to the negative 6, right? So about how many times larger is the 6 times 10 to the negative 6? About 2 times larger, right? What about 7 times 10 to the negative 8? 3 times 10 to the negative 9. Which one do you think of those is? So additional factors of 10 to the negatives means divide by 10 again, right? So it has to be 7 times 10 to the negative 8. Okay? This one is divided by 10 again, so it's another decimal away. Negative 9 is divided by an additional factor of 10. Which means, if I want to go 8, this would be 0.3 times 10 to the negative 8. That might be an easier way to think about it if we get an answer. Okay? Now here's what's really cool. We want to estimate how many times larger it is. Look what we can do. 7 times 10 to the negative 8 divided by 3 times 10 to the negative 9. When I have the quotient property, what can I do with my exponents? What operation? Cancel out or subtract, right? So I can do negative 8 minus negative 9, which is 1. I got that 70 divided by 3 again that we saw last time. So was that like 22-ish? 23-ish? All right. 70 divided by 3 is nicer to think about than 0.000000007 divided by 0.000000003.
It's 23.
So looking at number 1, we got to see how many times we got to move this decimal. All right? So 1, 2, 3, 4, 5, 6, 7, 8 M's. No, 9, 10, 11, 12, 13. So is everybody good with 3 times 10 to the negative 13th power? I had to move that decimal 13 times there. Right, Ryan and Vinny? Now, what needs to be on the largest part of my number line then? Sean?
10 to the negative 12.
Yeah, because that's the next factor of 10 bigger than where I'm operating. So that means each tick mark has to be 1 times 10 to the negative 13. 2 times 10 to the negative 13. 4 times 10 to the negative 13. Oh, yeah. By the way, this seems like a lot of writing, but it'd be way worse to write all the decimal point 0.0000000. Okay? So there's our tick mark. Next, we need the radius of this electron. Where is it located? Right there. At 3 times 10 to the negative 13. What does our factor of 10 need to be on our number line?
Negative 23.
Negative 23. All right, I'll let you guys get after it a little more here. Now that we have our scale, I'm not going to do them all. I know I'm going to 1.7. So this, I'm just going to do this is 1 times 10 to the negative 24th, 2 times 10 to the negative 24th, and 3 times 10 to the negative 24th. Because I know I just need to go to 1.7 right there. All right, 1.7 times 10 to the negative 24. That's where that's going to be located on our number line. So last little example to show you. We want this wavelength of A written as a power of 10. So if this is 6 times 10 to the negative 12, this has to be 6.1 times 10 to the negative 12. As a decimal, how many zeros are going to be in front of that 6? As a decimal, how many zeros in front of that 6?
Negative 12.
Well, if I move it, I'm going to put it once to put it right there. Then how many more moves?
12.
No, I already moved it once to get in front of the 6. So 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 6, 1. Which one would you rather write over and over?
Probably not.
Probably the first one. And that's the whole point of using these factors of 10. They're easy to work with for computation, and they're easier to write for efficiency. That's it. Big numbers, little numbers on a number line. We did it.